If the sun suddenly disappeared, Newton's theory of gravity predicts we'd feel it instantly. The Earth would immediately break orbit and fly off into space. But in 1905, Albert Einstein realized that kind of instantaneous action creates physical paradoxes. He overhauled our understanding of gravity, proving that it is actually caused by the bending of space-time. A change in gravity creates a ripple that spreads outward at the speed of light. This established the concept of locality, meaning the effects of any physical event must spread at a strict finite speed. There is a universal speed limit to cause and effect. Because of this delay, all observers will always agree on the order of events. Once Einstein fixed gravity, the absolute rule that nothing can travel faster than light became the bedrock of classical physics. Then came the 1927 Solvay Conference. The leading architects of the brand new science of quantum mechanics gathered to formalize their work. Quantum theory states that before a particle is measured, it has an associated wave function. This wave spreads out through space as it travels, representing the mathematical probability of finding the particle in any particular spot. The paradox appears when you make a measurement. When the particle is detected at a single point, its probability wave everywhere else collapses to zero, and it does so instantly. To Einstein, this was a severe problem. A measurement in one location instantly affecting a wave function infinitely far away requires an influence traveling faster than light, directly violating relativity. Niels Bohr, the most influential figure in quantum physics, offered a different perspective. Under his Copenhagen interpretation, asking what the particle was doing before you looked didn't make sense. The math predicted the laboratory measurements perfectly, and that was all physics needed to do. This created a massive ideological rift in physics. On one side stood the champions of a local, realistic universe bound by a strict speed limit. On the other stood the founders of a highly successful theory that openly relied on non-local, instantaneous connections. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published what is now known as the EPR paper. Imagine a high-energy event creating two entangled particles, an electron and a positron. They shoot off in opposite directions to conserve momentum and charge. Their properties must precisely balance. If one has a positive spin, the other must be negative. According to quantum mechanics, both particles exist in a blur of multiple possibilities until measured, but the moment you measure the electron spin, the distant positron is instantly forced to adopt the exact opposite state. Einstein famously called this spooky action at a distance. Einstein proposed a strictly local alternative. He argued that the particles don't communicate faster than light. Instead, they agreed on their states before they ever separated. They carry local hidden variables, like sealed envelopes containing pre-written instructions for how they will behave when measured. It was a thought experiment designed to logically expose the flaws in the Copenhagen interpretation. For decades, the physics community largely ignored the debate because both the Copenhagen interpretation and Einstein's hidden variables predicted the exact same laboratory results. There seemed to be no way to test who was right. That deadlock held until 1964, when physicist John Bell realized that Einstein's hidden variables hypothesis could be subjected to a real physical test. Bell introduced a crucial twist to the EPR experiment. Instead of measuring the particles on a single fixed axis, the experimenters at both ends get a choice. They can randomly measure the entangled particles along one of three different axes, say 0, 120, or 240 degrees. Quantum mechanics makes a rigid prediction for this setup because the measurement of the first particle instantly forces the state of the second. Measuring them on two different axes will result in their spins disagreeing exactly 25% of the time. Bell mapped out what happens if the particles use pre-packed local hidden variables instead, stating mathematically that no matter what internal strategy those particles agree on beforehand, if they are measured on different axes, their answers have to disagree at least 33% of the time. Bell had managed to draw a hard mathematical line. By counting how often the measurements disagreed, physicists could finally prove whether reality was operating locally or non-locally. The technology to actually run Bell's test didn't exist in the 60s, but eventually, researchers built highly complex equipment capable of firing pairs of entangled photons through rapidly rotating polarizers. Decades later, physicist Alain Aspect performed a series of grueling experimental tours de force to capture the necessary data. The results were undeniable. When the axes were different, the measurements consistently disagreed exactly 25% of the time. The data aligned perfectly with quantum mechanics. Einstein's local hidden variables were mathematically ruled out. The universe definitively contains influences that ignore distance and travel faster than light. If particles really do communicate faster than light, it invites a dangerous question. In relativity, faster-than-light communication allows messages to be sent back in time, creating severe logical paradoxes. But the universe has a built-in safeguard. When you measure a quantum particle, you will get a positive or negative result completely at random. You cannot control what the particle decides to do. Because the outcome is entirely random, it's impossible to encode a structured message. You cannot exploit the connection to send information to the other side of the galaxy. This leaves physics in an uneasy truce. Quantum mechanics violates the philosophical spirit of relativity with non-local action, but its inherent randomness protects the physical laws of cause and effect. There is one interpretation of quantum mechanics that manages to avoid faster-than-light influences altogether, the many-worlds theory. In this framework, a particle measurement doesn't cause a probability wave to instantly collapse across the cosmos. Instead, all possible outcomes physically happen. The observer becomes entangled with the particle, and reality splits into parallel branches for every possible result. Because both outcomes continue to exist, the particles don't need to communicate with each other across space to coordinate their states. Whether our reality relies on invisible, instantaneous links across the cosmos or an endlessly fracturing multiverse, one thing is certain: the true nature of the universe is far stranger than classical physics ever dared to imagine.